Let's take a look at another multi-force problem. This one looks quite a bit different, but you're going to see in a few moments that it's actually not that much different. We want to find the acceleration of this system where we have a 10 kilogram mass hanging off the edge and a 2 kilogram mass on the surface here with a force of friction of 20 newtons that's acting between these two surfaces right here. Friction's not acting here, right? Because this guy's not in contact with the surface. Friction's acting here. Not that it really matters where friction acts. In the end, friction's opposing the motion of the system. We want to find the acceleration of this system. Let's first name these objects. We're going to call this M1 and this one M2. Now, let's draw a free body diagram for this. Before you do, though, just let me finish up. Please don't write anything yet, okay? Because you're going to see something that in a few minutes, I think, is going to be a little bit easier than what I'm going to show you right now. I just want to demonstrate for you something right now. We've got a force of gravity acting down on this 10 kilogram object, right? Let's call that F2, or you might want to call it Fg, whatever you want there. In fact, I'm going to do that. I'm going to call it Fg. Fg2, the force of gravity acting on object number 2. And the value of that is going to be m times g, right? Now, what other forces do we have acting on this system? We got friction, right? Which way does friction act? Friction acts to the, friction's going to act to the left. Okay, I'm going to draw this right here. I'll just label what we have there. FF2, FF, I'll just call it, is 20 newtons. What's the acceleration of the system? Well, at this point, it would come time for step 2, right? Which is F net is equal to the sum of the forces. Again, don't write this down yet. I'll give you a chance in a bit here, okay? F net is equal to the sum of the forces. That would be FF plus Fg2. And then we would say m times a is equal to the sum of the forces, which would be FF plus Fg2. And then we start subbing in our numbers in. What mass do you think you'd sub in here? It would be the 2 or the 10? Or 12? 2, 10, or 12? Who says 2? Who says 10? Who says 12? It would be 12. We'd use the entire mass of the system here, 12 kilograms. Look, it's m times a. The net force, the total force, is acting on the system here. Now we're going to multiply that by the mass. What value would we use for FF? 20 newtons? Or would it be negative 20 newtons because it's acting to the left, right? Again, don't write this down yet, guys. What about the force of gravity? What mass would I use? It's m times g, right? What mass would I use? Would I use the 2? Would I use the 10? Or would I use the 12? I'd use the 10. The net force acts on the system, but the force of gravity directly is acting only on this 10 kilogram object. So we're going to say that's 10 kilograms times 9.81, or it's acting downwards, right? So that's going to be negative 9.81, isn't it? Make sense? This is why I asked you not to write this down yet. The force of friction we said is negative 20 because it's acting to the left. The force of gravity is negative 98.1 because it's acting down. The problem is those two forces are pulling against each other. They're opposing each other. And therefore, one of them needs to be a positive value. We got left negative, down negative, and normally that's a sign convention that we use. But since these guys are opposing each other, one of these guys has got to be positive. So here's what I suggest you do to help you to see that. What I suggest you do is turn this diagram into an easier, a simpler diagram. Take this 2 kilogram or this 10 kilogram mass, this mass number 2 here, and kind of pull it up like this, kind of straighten it out. And pretend you have a situation like this, where we have object number 1 that has a mass of 2.0 kilograms, and we have object number 2 attached to it like this, where we have a mass of 10 kilograms. If that's the case, then the force of friction is still going to act to the left, and it's going to still be 20 newtons. But the force of gravity acting on object 2 now is going to act this way. Does that make sense? Of course, gravity is not really acting to the right. gravity's really acting downwards. But if I pretend that this is on a flat surface and I pull object number 2 up like this, then object number 2 is going to be on the flat surface and FG2 is going to be pulling to the right. That helps us to understand a little bit more why this is going to actually be positive 9.81. My masses are all good there. It is 12 kilograms times the acceleration equals negative 20 plus 10 kilograms times 9.81, but we're going to make that force of gravity positive because it's, in my new diagram, acting to the right. Does that make sense? So let's figure this out now. We got 12 kilograms times the acceleration equals negative 20 plus 98.1, or 12 times A is equal to 78.1, and 78.1 divided by 12 gives me a value of 6.5 meters per second squared. Or you could say 6.5 newtons per kilogram. Now that seems like a reasonable number, right? If you have just gravity acting on the 10 kilogram object, that's all I got, a 10 kilogram object, and I drop it, it accelerates at 9.81. Well, this isn't going to accelerate at 9.81. It's going to accelerate at a lower rate than 9.81, right? Because A, you have this 2 kilogram mass that you're trying to pull sideways, and B, you got friction pushing it back the opposite way, right? So it's going to accelerate at some rate that's between 0 and 9.81. We get 6.5. Seems like a reasonable number. Let's try one more here. We've got a table this time that has 3 objects on it or around it. 2 little pulleys here. We've got an object in the middle that has a mass of 10 kilograms. It's attached to a string over here, which is attached to an object that has a mass of 20 kilograms. It's attached to this end to an object that has a mass of, let's make it 10 kilograms. There's going to be a force of friction acting of 50 newtons. We want to find the acceleration. Now, my suggestion here is to straighten this out. Okay, don't draw the free body diagram like this, because if you do, you're going to get mixed up with positives and negatives, just like we did in the last one. I drew it wrong on purpose in the last one, and everybody in here agreed with me that that was correct. Okay? I'm suggesting to you that if you redraw it, then everybody's going to agree with me when I have it drawn correctly, or when I have the signs correct. So let's first take this 20 kilogram mass and pull it out like this, stretch it out like this. That makes the surface, that makes the 20 kilogram mass on the surface like this, the 10 kilogram mass on the surface like this. Now let's take the other 10 kilogram mass, we'll call it mass 3, and let's stretch it up like this. If I do that, then I've got a third 10 kilogram mass like this. Now what about my forces? Well, there's a force acting on the 20 kilogram mass that's down, but when I stretch it out, it's like this. So I'm going to call this FG2. Sorry, FG1, I should say. The force of gravity acting on object number 1. It's really acting downwards, but I've got it drawn to the left in this diagram. Now, on the second 10 kilogram object, this is object number 3, we've got a force of gravity acting this way. I'm going to call this FG3. It's acting to the right. It's really acting down, but I'm drawing it as if it's acting to the right because that's going to help me understand the signs, the positives and negatives here. Which way does friction act? Which way does friction act? We're told that we have a force of friction of 50 newtons, but we're not told which way it's acting. Left or right? Well, which way is the system going to move? Yep, it's going to move to the left. Right, because the 20 kilogram object is heavier than the 10 kilogram object, it's going to move to the left. Therefore, friction is going to act to the right. Now, there is a force of gravity acting down on the 10 kilogram this way, and a normal force, but they cancel out. In these diagrams, I tend not to even draw those, just because it tends to clutter up the diagram a little bit more. So there we go. That's step 1. Step 2 is to say F net is equal to the sum of the forces, which is FG1 plus FF plus FG3. Then I say M times A is equal to the sum of those forces. Fg1 plus Ff plus Fg3. Now what's the mass here? What mass do I use? 20, 10, 10, or some kind of combination of those? The net force, the total force, acts on what? The system. And the system has a mass of 40 kilograms. So the mass that I'm going to use here in my M times A equation, the net force equation, is 40 kilograms. Fg1, what's that value going to be? M times G. What mass do I use here? 20, 10, 10, or 40? The force of gravity acting on the system is caused by the 20 kilogram object. So I'm going to say it's 20 times negative 9.81. Negative because it's acting to the left. Force of friction is 50 newtons, but I'm going to make the force of friction 50 newtons to the right, positive 50 newtons. And force of gravity 3, I'm going to make 10 kilograms times positive 9.81. Positive because it's acting to the right. Really, it's acting down. But I have to make it different than the first force of gravity because it's acting down but opposing Fg3. So two forces of gravity, both acting down but both opposing each other. It's like a tug of war. One's pulling against the other. We can't make them both the same direction if they're pulling against each other. So let's get this right-hand side now. 20 times negative 9.81 is negative 196.2. Subtract or add 10 times 9.81 is 98.1. Negative 98.1. I think it's negative 48.1. Negative 48.1 newtons. Now we're going to take that 40 over by dividing. I get negative 48.1 divided by 40. That's going to give me that negative 1.2025 meters per second squared. Is that right? Which is negative 1 point, to the right number of significant figures here, negative 1.2 meters per second squared. So which way does this system accelerate? With the way that I have it drawn the second time here, it's accelerating to the left, right? Because it's a negative value. So that means that object number one, the 20 kilogram object, initial 20 kilogram object, is going to go down, whereas the 10 kilogram object is going to end up going up. Does that make sense? All right, I'd like you to take a look now at worksheet number 12 that you were working on yesterday, but you're going to flip the page. And this time you're going to work on questions 5 through 9 for the next few minutes, please.